Today, we will consider a common example, a block on an inclined plane without friction. The angle of incline is theta. We want to find the block's acceleration. We start with the free body diagram showing the forces on the block. Gravity is acting downward, mg. We know the block won't move straight downward, so we expect there to be a normal force. However, the normal force won't be straight upward as we might expect from experience. In fact, it's called a normal force because in this context, the word normal means perpendicular to the surface. This is because the normal force is perpendicular to the incline. We will see more justification for why this is momentarily. Without friction, these are the only forces. At this point, it may not seem immediately clear how to continue because we don't yet know the magnitude of the normal force. To make progress, we can utilize an important technique, changing the frame of reference. Usually, we have the x and y dimensions as horizontal and vertical. However, this choice is arbitrary. Let's see what happens if we define x as being down the incline and y being perpendicular to the incline. With this frame shift, the normal force is now in the y direction. However, the gravity, mg, is at an angle. So, we need to split it into its components. The x component is down the incline, and the y component is into the incline. Notice how the two components make a right triangle with the original mg forming the hypotenuse. We do it this way specifically so we can employ simple trigonometry. We now need the top angle in this triangle. This angle equals the angle of the surface's incline. You can try to prove this fact for yourself geometrically, or click the link on screen or in the description to see that derivation. This angle in the triangle is theta, and the hypotenuse is mg. So, the x component down the incline is mg sine theta. The component into the incline is mg cosine theta. Now we're ready to set up Newton's second law for each direction. In the y dimension, the sum of the forces is the normal force minus mg cosine theta. This equals the block's mass times its y acceleration. Because the block doesn't move into or off of the incline, it doesn't accelerate in the y direction. So a sub y equals 0. Thus, the normal force equals mg cosine theta. Now we consider the forces acting along the incline. The only force present here is the x component of gravity, mg sine theta. This equals mass times the x acceleration. The masses cancel, and we're left with a sub x equals g sine theta. Because the y acceleration is 0, g sine theta down the incline is the only acceleration. If desired, we could use this acceleration along with the kinematic equations to find the properties of the motion down the incline. Soon we will use the technique presented here to solve for the motion when we have friction present, as well as more complex systems.